Welcome to Web Handling. My name is Dave Roysam. I am super excited to continue our new mini-series on measurements. In this clip, we discuss how many measurements you might need to support a working theory. I use the word support because you cannot prove or disprove a working theory with measurements alone. Instead, all you can do with measurements is to provide evidence one way or another. The answer is, of course, it depends. It may be one measurement or observation, or it may be 10,000, or more likely, somewhere in between. I know your time is precious, so let's get started. Troubleshooting is often an inductive, deductive, iterative process. Gather data, make a working theory, design a test for that working theory, do the test, analyze the test. If the theory tests well, to your statistical satisfaction, you may be done. If not, you will need to rework or redesign the working theory and repeat the iterative process. At every step of the trial work, we are confronted with the question of how many samples or measurements you might need. If you have too few measurements, the results will be statistically meaningless, and you will have to do it again or improve the trustworthiness in some other way. If, on the other hand, you have too many measurements, you cost the company more time and money than necessary. So the million-dollar question, literally $1 million in some cases, is how many measurements or observations is optimum to satisfy a minimum level of trust. The answer can be 1 or 10,000 or somewhere in between. A short trial may improve the initial guess of what is needed for a more determinative trial. But usually you will not know until the short or the full trial results have been thoroughly analyzed. The lowest number of trials or observations necessary for a statistically sound conclusion may be as little as one single observation, as given in this practical example. Here is a nearly continuously running coder. Prior observations shared by the operator is that they occasionally see a web break for reasons not yet known at the top of acceleration, but seldom at other times. Also, when it happens at other times, the cause is usually known. The unknown web break could be elsewhere in the startup ramp, and the principle would be the same. Note that the runtime between down is about 1,000 minutes on the average for a continuous coder. Yet the acceleration itself is only about 1 minute long. The odds of unknown web breaks favoring the ramp by sheer coincidence is very remote. Very, very remote. So something about the ramp is risky for web breaks. But if we look a little bit closer, we find that the break occurs very near the 1 to 3 second long rounding part of the S-curve ramp. Now, we can be pretty sure that there is something wrong with the S-curve drive programming. In fact, well-informed web handlers and drive experts alike should know that this is a very risky time for drive tension control quality. We should not be surprised to see tension variability at that time. We would next turn to very fast data recorders of load cell tension and drive motor readings in that section to inform better drive tuning parameters. In short, a single observation during a short event may be enough to be pretty sure what to do next. I will also mention that there are certain defects that are almost uniquely defined as to the root cause mechanics when the physics are well known, as they are for many web handling areas. Here, I will offer that a single observation of the common wound roll corrugation is usually more than enough to indict web thickness profile variability, as there is almost no other known way to make that defect. However, we must all have humility in making conclusions based on even statistically compelling observations. I was once troubleshooting a wrinkle and pointed to its source to my host. He could not tell what I was pointing to, so I touched the point on a web path diagram posted on the framework. At the instant I touched the diagram, the web broke. Obviously, this is sheer coincidence, no matter how remote that coincidence might seem. This has to do with the law of large number. If you pay close attention to dozens or hundreds of items every day for decades, you will personally experience hundreds of very compelling coincidences. On many, many occasions, I only needed 4 pairs of very simple observations or measurements to be pretty sure of a connection. In this specific example, all 4 of the wrinkle samples had a lower weight than all 4 of the unwrinkled samples, all chosen somewhat randomly by whatever was closest. Finally, lest you ever think your trial work might be short, let me give you a well-documented example where sample sizes might need to be in the thousands, especially when dealing with customer complaints, as we will see. There is a landmark study by Seth and Page who were studying web break complaints at their paper printing customers. The printers believed that some suppliers had better paper than others with respect to runnability or web breaks, using very solid statistics. Seth and Page demonstrated that sample sizes in the thousands would be needed to make any such conclusions of which supplier was better than another with respect to web breaks with any sort of trustworthiness. That made the monthly web break report that most paper mills were following worse than worthless. These monthly management reports may be meaningless or even give the wrong impressions. This is all due to insufficient sample size. The details of things like this will vary with every customer in every situation. In this specific case, the seasonal moisture variations at the customer dwarfed any paper supplier differences. In any case, however, the customer's process itself adds an incredible amount of noise to an already complex and noisy system. Worse yet, as I teach in my troubleshooting class, you may not necessarily be able to trust most observations shared by the customer, whether they be defect diagnostics or comparing your performance with a competitor. All you know for sure is that they are unhappy. All you know for sure is that you need to get on an airplane and go to see firsthand what the problem is and use your best troubleshooting and your best people skills that your company has. There are 4 starting points for a more detailed discussion of problem solving, including sample sizes. The first is a very obscure but very well done, self-published 150-page book. Here, Paul Frost teaches us just how little you might be able to statistically conclude from the very common top-of-the-roll sampling that is every day in web tests around the world. The second is my industrial problem-solving book that is a good companion to my industrial problem-solving course of the same name. The third is the must-have 750-page Web Handling Handbook, written by myself, Tim Walker, and Dylan Jones. This is where we would look for the targeted and objective measurements for most web enroll defects that are science-based, that can help you going on unnecessary and fruitless fishing expeditions. Last but not least is my award-winning and trademarked Web 101 class that has been taken by about 5,000 people, just like you. Here you will learn about web handling, winding, common converting operations such as slitting, as well as a good sprinkling of problem-solving techniques. Thank you so very much for joining me in this Measurement Miasma mini-series. Please join me in the next clip where we will talk about nonlinear response. If you have a topic you would like to hear about, let me know in the comment section below. If you found anything interesting or useful here, please like and share and subscribe. See you next time.